A finite element bearing capacity analysis of layered soil deposit reinforced with stone columns. Abstract. In the present study, an attempt has been made to comprehensively investigate the bearing behavior of a rigid and rough circular footing placed over a layered soil deposit, reinforced with stone columns. For the analysis, a series of finite element analyses has been carried out to obtain the failure load as well as to understand the failure mechanism. For all the analyses, end-bearing column has been considered by assuming it to be resting on a rigid bedrock. Influence of several critical parameters, such as ratio of undrained shear strength of topsoil to that of bottom soil, diameter of stone column, thickness ratio of top layer and angle of internal friction of stone column aggregates, on the overall bearing capacity response has been comprehensively investigated and reported. Obtained results and the corresponding governing mechanism has been comprehensively explained. Based on the results, it has been found that for a stone column reinforced layered soil deposit, for a depth ratio of more than 2, the influence of bottom soil diminishes and undrained shear strength of topsoil governs the bearing capacity. Similarly, increment in the bearing capacity due to increase in column diameter as well as angle of internal friction of stone aggregates have been duly quantified and represented in graphical form. Present study would be highly beneficial for practicing geotechnical engineers while designing a shallow foundation for transmission towers over a layered soil deposit. Keywords: finite element analysis, stone column, layered soil, Plaxis. Introduction. While designing a shallow foundation for a structure, two criteria must be satisfied, i.e. it should be safe against failure and settlement corresponding to the working load of the superstructure should lie within the permissible limits prescribed in various design codes. Substantial effort has been applied in the field of classical geotechnical engineering to satisfactorily answer the problem of bearing capacity of a shallow footing placed on a homogeneous, semi-infinite ground surface based on limit equilibrium approach 1, 2, 3, 4 limit analysis method 5, 6, 7, 8 and slip line theory 9. However, often the shear strength of underlying soil, and consequently ultimate bearing capacity of shallow footing may not be adequate to support the external load coming from the superstructure. Under these circumstances, a geotechnical engineer may design a deep foundation. However, designing a deep foundation incurs a significant cost and consequently the overall cost of the project exceeds substantially. Under these conditions, ground improvement technique, such as installation of stone columns, may yield an alternative solution to the foundation engineer to enhance the strength of the soil and also to reduce the differential settlement and yields and enrobement in the bearing capacity of the foundation. Reinforcement of soil using stone column has gained wide popularity to enhance the shear strength of soil and to reduce the compressibility of the soil. Several researchers 10, 11, 12 performed laboratory investigation on stone column reinforced geomaterials and established the efficacy of stone column in improving the overall bearing capacity of the footing. However, in all the previous analysis, a single layer of homogeneous semi-infinite soil deposit has been considered. Furthermore, the relative influence of several critical parameters, such as ratio of undrained shear strength of soils, column diameter, and relative compactness of stone column has not been considered explicitly under a single title. Therefore, in the present study, the efficacy of stone columns in improving the bearing behavior of layered soils has been considered explicitly by considering the influence of several critical governing parameters, such as ratio of undrained shear strength of topsoil to the bottom soil layer, Cu1/Cu2, stone column diameter, d, thickness ratio of topsoil layer, h/b, where b equals footing width, and friction angle of the stones of the stone column, dot. A finite element model has been developed in commercially available software package Plaxis 2D. The relative influence of each critical parameter has been presented in graphical form and the influence of variation of parameters on the overall bearing capacity and the corresponding failure mechanism has been discussed in details. 2. Problem description and material properties. A schematics of the problem. To model the geometry of the problem, axisymmetric analysis has been performed in Plaxis 2D due to the symmetry of the problem. Schematics of the problem geometry considered in the present study has been shown in Fig. 1. The lateral and vertical boundaries are selected such that the stresses generated during loading are well confined within the boundaries of the problem. In the bottom boundary, both horizontal and vertical fixities were applied while lateral boundaries were restrained in horizontal direction. A fine mesh refinement was adopted based on a mesh sensitivity study. B. Material properties. In the present study, two different clay layers have been adopted. Properties of the soil layers have been adopted from pertinent literatures. For stone columns, the geotechnical properties were adopted from 12. The properties of the clay and stone aggregates has been summarized in Table 1. 3. Numerical analysis. As already mentioned, the numerical analysis has been carried out using the commercially available software package Plaxis 2D. It is a very useful tool to solve the complex problems of geomechanics involving stress deformation-based analysis 13,14. Footing has been modeled as having sufficiently high rigidity. A rough interface between the footing and soil matrix was modeled to ensure a rough footing behavior. The finite element model and boundary condition for the half model has been presented in Fig. 2. 4. Results and discussions. A. Influence of undrained shear strength ratio, Ussr. To understand the relative significance of ratio of undrained strength of top layer to bottom layer, a series of investigations were carried out to study the relative influence of parameters on the overall bearing capacity of the footing. Analyses were carried out for 5 different Ussr values. Variation of bearing capacity with Ussr has been presented in Fig. 3. As depicted in Figure 3, ultimate bearing capacity, UBC, exhibits a linear trend with increase in Ussr. This may be attributed chiefly to the fact that as the undrained shear strength of the topsoil increases, the passive resistance to the footing against the external load increases proportionally. Therefore, an almost linear increase in UBC with Ussr has been observed for all the cases considered in the present study. B. Influence of diameter of stone column, D. To investigate the influence of stone column diameter on the overall bearing capacity of the layered soil deposit, analyses were carried out for 5 different column diameters, viz. D equals 0.2, 0.4, 0.6, 0.8, and 1.0 m. Variation of UBC with D has been shown in Fig. 4. A gradual increase in UBC of foundation with diameter of stone column was observed within the range of stone column diameters considered in the present study. It may be noticed that up to a diameter of 0.6 m, UBC increases almost linearly. As the diameter increases beyond 0.6 m, a steep rise in UBC of the soil deposit takes place. It may be primarily due to the fact that as the diameter of the stone column increases, the percentage of stress transferred to the stone columns, by the external load, increases. As stone columns are stiffer and have substantially higher shear strength than the adjacent soil mass, therefore the UBC increases nonlinearly for high range of stone column diameters. See influence of thickness ratio of topsoil, H/B. Thickness of top layer of soil was varied to understand the influence of thickness of topsoil layer on the overall bearing. Behavior of stone column reinforced ground. 5 different thickness ratios, H/B equals 0, 1, 2, 3, and 4, were considered. Variation of UBC with thickness ratio has been presented in Fig. 5. It may be seen that UBC increases with increase in the thickness of topsoil layer. It was anticipated as in the present study, undrained shear strength of the topsoil has been assumed to be higher than that of the underlying soil layer. However, it may be noted here that as the thickness ratio achieves a value of more than 2, the influence of layered deposit of soil diminishes and the UBC of footing tends to assume a constant value. It may be primarily due to the fact that as the thickness of topsoil layer increases, the stress distribution gets mostly confined within the topsoil layer and plastic zone does not propagate up to the bottom soil layer. D. Influence of friction angle of stone column. This analysis aims at obtaining the influence of friction angle of the stone aggregates of stone columns on the overall bearing capacity. In the analysis, 5 different values of angle of internal frictions, equals 26 degrees, 30 degrees, 34 degrees, 38 degrees, and 42 degrees, were considered for a stone column diameter of 0.4 m. Variation of UBC with friction angle has been presented in Fig 6. As could be seen from Fig 6 that the UBC of stone column improved soil increases with increase in the angle of internal friction of the stone aggregates. The variation of UBC with friction angle is somewhat nonlinear and the rate of increase of bearing capacity increases as the value of angle of internal friction increases. V. Summary and conclusions. In the present study, a comprehensive study has been carried out based on a series of finite element analysis on a stone column reinforced layered soil deposit. Efficacy of addition of stone columns on the bearing capacity behavior has been duly considered. Influence of several governing critical parameters on the overall bearing capacity response of the system has been investigated and results are presented. A proper explanation has been provided with each obtained results explaining the mechanism behind the obtained observations. The major conclusions of the study may be summarized as: in a layered soil deposit, reinforced with stone column, the undrained shear strength of the topsoil governs the overall bearing capacity of the system for a depth ratio, h/b, more than 2. For h/b less than 2, the undrained shear strength plays a substantial role in the overall bearing capacity. Bearing capacity increases linearly with increase in the undrained shear strength ratio, Ussr, within the range considered in the present study. And gradual increase in bearing capacity has been obtained with increase in the angle of internal friction of the stone aggregates of the stone column. As the column diameter increases, the bearing capacity increases nonlinearly due to the larger resistance of the external load by the stiffer stone column aggregates.